with Mark Weil, who is one of the experts in the theory of quantum communication, and he's here to share some of this knowledge with us today. And he's originally from Waterloo. He did his undergrad and master's there, working with KKD, and now he's working in the United States with Mark. He is here due to a grant that was given by the American Physical Society in partnership with the Brazilian Physical Society. And we are really happy that he is here today. Thank you.
Thank you very much, Barbara. And thank you to everyone for coming. It's my pleasure to be here. I also want to thank Rafael for organizing all of this, and also to Barbara for the hospitality here. So the topic of this course is, as Barbara said, quantum communication. So I think online there is an outline of the course with all the topics. It's kind of ambitious, but I hope to cover as much as we can. And I hope this is also kind of informal in the sense that we can have a bit of a conversation. So you ask questions because this is really for you. So please ask lots of questions. Please don't be hesitant to interrupt me. So it is not really that important that we cover absolutely everything, but it's important that whatever is covered is can be understood. Okay. Thanks. So for this first lecture, probably what I'll do is just go through some of the basics of quantum information theory before getting to the real sort of communication part of it. So there are many textbooks now on quantum communication. So let me just mention that I have a website. And if you go here, I have lots of resources on quantum information and those types of things. I will just mention the book by, say, Nielsen and Chuang. So there's Nielsen and Chuang. There's also the book by my advisor, Mark Wilde. There's also a book by John Watrous. And there are many others out there as well, but these are some ones maybe to start with. So before I get into the actual quantum information background, maybe I'll just provide some overview of what this course is about. Right? So I said that it's about quantum. So it's quantum communication is the title. So let's break this down. So what does that mean? So we have this communication part. So typically what we do is we want to talk about communicating information from one person to another. So they could be far away, separated, and we want to be able to send information from one party to another. So what kind of information is that? So in quantum communication theory, we can typically consider three types of communication. So it's like classical. So it's like classical communication. We want to communicate bits. And the sort of standard protocol that we have for this is something called superdense coding. So is my writing okay? Can everybody see it, legible? Okay. So this is a standard protocol which we'll go through in this class. So this is a protocol for classical communication with assistance of entanglement. We also have quantum communication in the sense that we want to transmit qubits instead of just classical bits. And there's a standard protocol for this, which is also known, and it's called teleportation. And this also makes use of entanglement. So this is also like entanglement-assisted protocol. And there's another kind of communication which is perhaps the most immediately relevant for practical applications, and this is private communication. So here, the goal is to basically transmit private information, so information that is secret from some third party or an eavesdropper. Okay, and the standard protocol we have there is basically QKD, so quantum key distribution. Okay. So this is essentially the communication part. So what do we mean by communication? This is what we mean. So we have these three types. And then there's the quantum part. So when we say quantum, what exactly does that mean? So it means that in order to accomplish these tasks of communicating either bits, qubits, or private bits, the goal is to use quantum strategies. So quantum strategies means we make use of properties of quantum systems. So we make use of quantum systems for the actual protocol, and we make use of certain properties that quantum systems have. So we make use of things such as superposition, entanglement, which I mentioned already, right? So primarily, these are the things that we want to use. These are the sort of uniquely quantum properties that allow us to, that we make use of in order to actually call it quantum communication. All right? So let's see if I put this up. Okay. Okay, so in the ideal situation, when we talk about communication, communication occurs over what is called a channel. So a channel is some kind of physical medium that connects the sender and the receiver. And usually for the sender, we call the sender Alice, and we call the receiver Bob. And what's connected between them is some physical medium that allows us to actually transmit the quantum systems or whatever it is, whatever the signal is made of from the sender to the receiver. So in the ideal situation, what we would have is an ideal quantum channel where if Alice has some state, quantum state, which you call psi, that she wants to send to Bob, then she can encode this in some way into some quantum system. So she prepares a quantum system in this state, and she sends it over the channel to Bob. And in the ideal case, what we would have is the same pure state arriving on Bob's side. So this is in the ideal case. But perhaps we all know that quantum systems are very fragile. So what does that mean? So it means that they're very susceptible to interacting with their environment. So instead of this nice ideal situation where the state that is being sent is the same one that is being received, along the way, there's some interaction with the environment. So what happens is there's some environment, and the environment is also in some state, right? So that state comes in here, and there's some interaction here between between the system and the environment. All right, so right? And what this means is, so the system will interact with the environment, and the state that comes out will not be the state that was initially sent, but it will instead be some mixed state. Okay, so we will define all of these terms precisely, but this is just to give some broad overview. So what ends up happening is there's some interaction with the environment, and what that amounts to is that the overall noise that is induced by this interaction with the environment means that there are errors in communication. So the state that was being sent is not the one exactly arriving, so there are errors in the communication. And we describe these errors, we characterize them with what's called a quantum channel. Okay, so we say that, so mathematically we would write like this. So we'd say rho we write like that, right? So this is a mathematical object that it will take as an input state, some state that Alice wants to send to Bob, and what comes out is something else, right? And one of the tasks is to basically measure how close the initial state is to the final, okay? So the point is that instead of having an ideal quantum channel, we always have something that's noisy. And the goal in quantum communication is to try to fight the noise. So how do we fight the noise? So we want to fight the noise in the sense that we want to come up with some protocol, some strategy, not just to send directly the information that we want over the channel, but to do something better, right? So what does that mean? So ultimately, by fighting the noise, we mean we want to simulate an ideal channel. So okay, so and what are the resources that we have to do this? So the first thing that we have is maybe we can use this channel multiple times. So we can have some kind of encoding. So instead, if you want to send 1 qubit, instead of just sending 1 qubit, we first encode the information in 1 qubit into several qubits. So we create redundancy in our data, and then we pass that through the channel in such a way that so that it can be decoded with higher success. Okay, so multiple channel uses and local encoding and decoding. So encoding is something that Alice does in her lab, and decoding is something that Bob does in his lab. And we can also allow classical communication between the two parties. So typically for quantum communication, what we usually consider is that the classical communication between the sender and receiver is for free. So it's really the quantum information that we care about, and we just assume that the classical information, the classical communication is for free. Okay. So this is basically a broad overview of how we want to construct a communication protocol. So let me just draw a rough sketch of this now. So say we have our initial state psi. We have now some encoding on Alice's side. So this is going to be, again, some kind of map that takes one of these qubits to several qubits. Okay, so now each one of these qubits coming out of this encoding is sent through the quantum channel. And then on Bob's end, there's a decoder. So here, let's call this decoding. And yeah, so now the decoding just takes one of these. And now we want to see how close the initial state is to the final. So that is a basic question that we ask in any of these types of communication types, so for classical, quantum, or private. So this is the main question that we ask. So our figure of merit is essentially quantifying the distance between the final and the initial state that was being sent. Okay, and the goal is to fight the noise in such a way so that we can obtain the highest rate possible. So by rate, so here, the first goal is to fight the noise, right? But alongside that, so we want basically the error to go to 0. So zero error. But the second goal is to obtain the highest rate. Okay, and by rate, we mean, so it's either bits, so whatever unit of information that we want to send per channel use. So it's like either bits per channel use. So these are the two goals. And what we will try to go through in these sort of 5 classes that we have is outline some of the main theorems that are known for these types of communication tasks. So for classical communication, quantum, and private communication. So what is the highest rate given some quantum channel? So the main thing is that we have some quantum channel connecting Alice and Bob, the sender and the receiver. The question is, given that channel connecting Alice and Bob, we allow them to use this channel multiple times. We allow them to do some encoding and decoding at their local labs. The question is, what is the highest possible rate of communication? And this is important because, for example, in the case of QKD, we can design devices that can try to achieve the highest possible rate of private communication. So that's one motivation for it. Okay, so is this okay? This is just a general broad overview for now, just to sort of set things up before actually getting into the details. All good? Okay. So it's probably good now to set up some of the notation and just go through some more of the basic background on quantum information so that we're all in the sort of on the same page. So, okay, so let me first start by just talking about quantum states. Okay, so the basic unit in quantum information is the qubit. So qubit is a 2-level quantum system. So the thing is, in quantum information, we usually don't care about the actual physical system involved in most cases. We just take a more abstract point of view, and we just say that we have some, system that can take on 2 values, 0, 1. But the key feature in quantum mechanics is that we could also have a superposition. So we could also have a superposition of these 2. So concretely, we can imagine that this is like this. So this is just a column vector. So that we get where where this is the sort of normalization condition. So these represent probabilities, probability amplitudes. So what this is telling me is that if I were to take a system that's in this state and I measure it in the sort of 0-1 basis, then the probability of obtaining the outcome corresponding to 0 is the modulus squared of alpha. And the probability of obtaining the outcome corresponding to 1 is the modulus squared of beta. Okay, so hopefully this is sort of familiar from basic quantum mechanics. Usually in quantum mechanics, as we learned it initially, there's some Hamiltonian, and the task is to solve the Schrodinger equation and then obtain the eigenstates of the Hamiltonian, and then we usually want to measure the energy. So in those cases, we can think of these 0 and 1s as being like the energy levels of some Hamiltonian, and then when we do a measurement, these values actually correspond to the energy of the system, or the probabilities of obtaining those values for the energy. So now this is different from regular bits, because if we take this and we sort of draw it pictorially, what we get is what's called the Bloch sphere. So the two states, 0 and 1, are at the poles. And we define 4 other states. So here we have what we call the plus state. So here this is called a Bloch sphere. So ultimately, what this tells us is that a qubit, so any state of a qubit can be described as a vector in a 2-dimensional Hilbert space, or a 2-dimensional vector space. So and for a qubit, we have this very nice representation of a qubit, which is just as any state on the surface of the sphere can be written in this form for some choice of alpha and beta. And then we can also have, as I'll talk later, states that are inside the sphere. So those are called mixed states. Okay, so this is just for qubits. So, but we also have qudits. So qudits are basically just taking 2 and increasing it to some other d that's greater than 2. So we have some system where the sort of generic states are from 0 to d minus 1. And the important fact here is that these states and also here, they form what's called an orthonormal basis. So if we take I, so for all okay, and we can write any state and we can write any state or any state vector as where these coefficients, C, they are complex numbers. And same here, they are alpha and beta here are also complex numbers. And we have this condition, which is basically telling us that the probability of observing our quantum system in one of these states, as in when we do a measurement, we will observe one of these states when we do the measurement, which means that the probability is 1. The total probability is 1. Okay, so one thing I should mention is that for this entire course, we will just deal with finite dimensional quantum systems. So this D is always finite. So it is also possible to look at systems that are described by infinite dimensional Hilbert space. So these are systems of bosons, like photons. These are actually quite important for communication, but for the sort of laying the basic groundwork for the theorems that we consider, it suffices to just consider the finite dimensional case so that we don't get caught into too many technicalities relating to infinite dimensional Hilbert spaces. So I think in terms of getting the basic ideas, it is sufficient to just look at finite dimensional Hilbert spaces. Okay. So what I've described right now are what are called pure states. So it's pure state in the sense that it is just a vector in the Hilbert space. But there's a more, I guess, there's a more general notion of a quantum state. So suppose, say you in your lab, or Alice, someone in their lab prepares a quantum state, or they have some system, but they prepare it in some state with some probability. So here we're going to talk about mixed states. So with right, so there's a probability with some probability p sub I, Alice prepares a state psi. Right? And she sends it to Bob, but she does not tell Bob which one of these states she prepared the system in. Okay? So in this situation, we want to now ask the question, what is the state of the system from Bob's point of view? Right? So this is somehow a mixture. So to Bob, the state is actually unknown because this classical label I has not been told to him. So Alice just prepared one of these states and did not tell Bob which one it was. But he knows that it was prepared in the ith state with some probability pi. Right? So the state corresponding to this type of situation, and usually we will denote this type of thing with this notation. So we'll say that it is and we'll call this an ensemble. So the state corresponding to the ensemble the state corresponding to the ensemble is just going to be this. So it's just a random mixture of each one of the quantum states. And so we call this a density matrix. So sometimes we call it density matrix or density operator. Okay. And so what are the properties? So the key properties Yeah, and we also call them, I guess, mixed states. So as I said there. So we call it a mixed state because it's like a mixture of the different states. And it's like we don't have, it just corresponds to a lack of knowledge of which one of the states that the system is actually prepared in. Okay, so the mixed states are Hermitian. Means that, this is the dagger. It means just complex conjugate transpose. So that's equal to itself. So it means it's Hermitian. It's positive semi-definite. So this means that the eigenvalues and one more, yeah, so and the trace is 1. So the trace is just the sum of the diagonal elements when we write it as a matrix. Okay. So these are the properties of a density matrix. And the most general state of a quantum system, we would say, is a density matrix. And in terms of the Bloch sphere, this is something that, so any pure state can be described as on the surface, and anything that is mixed will be inside. In particular, if we have the origin of this sphere, the origin of this sphere is an important state as well. It's called the maximally mixed state. So it is just like identity over 2. Right? So this would correspond to the case where the p sub i's are just like 1/2. So in this case of a qubit, it's 1/2, and it's like the rho sub 0 or psi sub 0 and psi sub 1 are just any 2 orthogonal states, any 2 states which are orthogonal to each other. That would give you a maximally mixed state. Okay. So now when we have, this was all for in the case where we just have one system. But the more interesting case is when we have 2 systems, because then we can start to talk about entanglement. So when we have 2 systems, so we say they are bipartite systems. So you have bipartite systems. So these are described by the tensor product Hilbert space. So if you have 2 systems, or we have 2 parties, Alice and Bob, they each have a quantum system with the Hilbert space HA, and Bob has one HB. Then if you want to look at their quantum systems in total, then mathematically we describe that by the tensor product of the Hilbert spaces. So what does this mean exactly? So if we have an orthonormal basis for Alice's quantum system, so I'll write that as ONB, and we have another orthonormal basis for Bob's system. Then for the joint system, we just take the tensor product. So now we can think of this in terms of column vectors. So if we had, say, we have this as 1, 0. And so if you were to do 0, then this would be like taking what is called the Kronecker product of the matrices. So this would be, so here it's like we take each element of the first vector in this tensor product and we multiply it by elements of the second one. So it would be like 1 times 0, which is 0, 1 times 1, 0 times 0, and 0 times 1. So now this becomes a 4 by sort of 4 element column vector. So this is so this becomes an orthonormal basis for the tensor product. And if we have any state in this joint system, so say we have, first of all, a pure state. So if we have a pure state that's written in this form, then we call this a product state. And any state that cannot be written in this form, for some phi and, yeah, so for any two of these types of states, then we call it entangled. So okay, so it's called entangled if it is not a product state. So if it can't be written in this form. So what is an example of something that can't be written in this form? So let me just write it here. So we take two qubits. So Alice and Bob are both qubits. And we consider the following state. Okay, so you can show that this is entangled. So one way to see this is, because this is a qubit, we can do it in a slightly simple way, which is that any state that we have, any generic state, we can always expand it in this orthonormal basis. So we can always write any as right, for some alpha, beta, gamma, and delta in this way. Right? And you can show that there will be no alpha, no values of these coefficients that can give you this state if we demand that the state be a product state of this form. So that's something that you can try to show. And we call this state Bell state. So this state comes up basically in all of the communication protocols that we consider. So it comes up in teleportation, it comes up in superdense coding, it even comes up in quantum key distribution. So this is very important. And this is actually a state 1 of 4. So we also have the corresponding one with the minus sign, and we have 2 more. So altogether, these form the Bell states. And not only are they entangled, but we also say that they are maximally entangled. So this has to do with the fact that if you evaluate certain entanglement measures on them, for example, the entanglement entropy, then you get the highest possible value that you can get for that measure. So I'll leave that for now as that. Okay, so let me talk about mixed states. How is the time? Is it okay? Okay. All right. So what I just talked about there is the entanglement of pure states. We can actually say a little bit more about that. So one basic question is, given some quantum state on a bipartite Hilbert space, we want to know whether or not it's entangled. So this is actually an important problem. It is largely still an open problem. Only in certain cases can we actually solve that question. And one case in which we can solve it is for the pure states. And this has to do with basically what's called the Schmidt decomposition. So basically what this is telling us is the following. So if you have any Okay, so if you have any pure state, any state whatsoever, it is always possible to come up with a decomposition that looks like this. Okay, and we call this a Schmidt decomposition of the state. So here R is called the Schmidt rank, and these lambdas, they are called Schmidt coefficients. Okay, so I will not go through the proof of this here just for the sake of time, but it's actually straightforward to prove this using what's called singular value decomposition. So this is something that might be familiar to you from linear algebra. So this comes from, so basically, this comes from singular value decomposition. So if you are interested in seeing the proof, we can maybe go through it together afterwards. But for now, I'll just state this as a fact. But this is nice because this can tell us now right away when a pure state is entangled or not. So all we have to do is find the Schmidt rank, basically this R. Okay, so if so actually this is if and only if. So yeah, so this state is entangled if and only if this R is strictly greater than 1. So we can see that if R is equal to 1, it means that there's only one element in the sum, right? And if this element, if there's only one element of the sum, then this lambda k, by normalization, has to be just 1. And so then we immediately have a state of this form, which is a product state, right? So in that case, we know that it's separable. And because any state can be decomposed in this way, we get the reverse direction as well, because you can always do this type of decomposition. I guess one thing I should say is that the sum of lambda k is 1. Yeah. Okay. So is this okay? Any questions about anything? Have people already seen some of this? Maybe new, not new? Okay. All right, so this was the entanglement of pure states, but okay, so now let's do mixed states. So for mixed states, how do we define entanglement? So here we define entanglement for pure states. For mixed states, we have so if you have a state that's of this form, then we call it separable. And if you have a state that cannot be written in this form, then it's called entangled. So okay, so now again the question is, given some quantum state, when is it entangled? So in general, this problem has not been solved, but there are in some special cases the answer is known. One direction actually we do know in all dimensions, so it's called PVT criterion. So this tells us that if okay, so this criterion states that if the state is separable, then its partial transpose is positive semi-definite. Okay, yeah, and this is true in all dimensions. So now, what is the partial transpose? So let me just briefly say what that is. Right, now this fact is important because if we take our given state and we take the partial transpose, we find the eigenvalues, and when the eigenvalues is negative, then we know that the state is entangled. So that's why this is important, right? Because we just take the reverse implication. So maybe I'll write that. So if, or I'll just write it up there. It's clear. Okay, so if okay, so now what is this partial transpose? So if you're given some state, so let's start more simple with some matrix, right? So if you have a matrix, say M, then we can always write it in terms of its matrix elements in this way, right? So here, I is a column vector, right? In the ith element, we put a 1, right? And so if we take, so this is a ket. So now if we flip this and we make it into a bra, then it becomes a row vector, like that, right? And we have a 1 in the ith slot, right? So using this kind of decomposition, we can take any matrix and we can expand it in this way, and these are the matrix elements. Now the transpose of this is simple. We just switch the row and the column. So we just, right, this is transpose. Okay, so now, and then we can do this for any quantum state as well, because a quantum state is just a matrix, density matrix, right? So if you have a bipartite state, we can also expand it in this way. So we have and then the partial transpose is now similar, except we only flip the ones corresponding to the second Hilbert space. So if this is A and B, so we can also write this as So we just flip what's on the B. Bigger? Okay. Should I write this one bigger? Is this one okay? Yeah, so this is the prime. Yeah, this is also a prime. Sorry, yeah. So yeah, here we have the prime, but here we don't have the prime. But here the prime is there. And also here is the prime. Okay, so all of this is just to explain what this condition means for a mixed state. And if we have A and B either both qubits or one is a qubit and one is a 3-level system, then this condition is necessary and sufficient. Okay, so in this case, the reverse direction also holds, right? So in general, what might happen is that if it's entangled, then it could still be the case that this condition holds in general. But if you have two systems, both of which are either a qubit or one is a qubit and one is a qubit, then this condition is necessary and sufficient. So it cannot happen that entangled states satisfy this condition. Okay? So I'll just write that here. All right, so one more thing that I'll mention is the concept of, so we talked about trace, or we talked about partial transpose, so now let's talk about partial trace. Briefly talk about that. Okay, so you have the trace. So I think we are familiar maybe with what the trace is. So the trace is the sum of the diagonal elements. So if you have a matrix that looks like this, in some expansion, then we take the trace of that. Then it is just, yeah, so we can write it like this. So what we do is we take the trace of this is just that. But we have here an orthonormal basis. So this is just a Kronecker delta. So then we just get the sum of the diagonal elements for the trace. Okay? So now the same thing is going to happen when we have bipartite states. So here we would want to take the partial trace. So this physically, this corresponds to a situation where you have some quantum system. It could be entangled with something else that maybe you don't have access to. So how do you describe the state of your system then? So the state of your system would be described by just the partial trace over the system that is inaccessible to you. So if you have some state rho AB, another way to think about this is suppose Alice and Bob are sharing some quantum state, and Alice wants to do some measurement on it. And she wants to be able to describe the outcomes of her measurement without necessarily knowing the full state. So the question is, how can she do that? So mathematically, the way this is done is using the partial trace. So because Alice doesn't know the full state, because she might not know the state of Bob's system, or she doesn't have that knowledge, we just take the partial trace. Okay? And this is what it is symbolically, but we just do exactly what we did here. We have this in this form, so we so here we're tracing out the B part, so we just leave this part alone. And basically we contract just the B part here. right? So initially, we started with a matrix that is, I guess, right? So this is where dA is the dimension of A and dB is the dimension of B. So this is a matrix, square matrix of this dimension. And now when we take the partial trace, so we are left. Yeah, so we are left with something that is just sort of dA by dA. So I'll just write that here. So, okay. All right, so one way in which this partial trace is important is because of the fact that we talked about mixed states as being some density operator, but it is always possible to think about some mixed state as being in a pure state with some system that is inaccessible to you. So if you have some state, some quantum system, which is in the state rho sub A, then we can always think of this as being in a pure state with some reference system that is inaccessible to us. So, and we call this the purification. Right, so we can also think of this R as being some kind of environment. So maybe I'll just call it an E. So we can say that any mixed state okay. So one easy way to sort of view this is the following. So if we have a decomposition of the state, so we consider these to be the eigenvalues. So we call this the spectral decomposition. These are the eigenvalues. These are the eigenvectors. Then we can construct this one as follows. So as in this way, right? And this is a pure state, right? And you can show that using what I showed about the partial trace, you can show that if you trace out so if you do the partial trace of this state on the E system, then you'll get back this. So this is something that you can show. Okay. So, all right. So I have about maybe half an hour. So I think that's fine. So now I'll talk about measurements. So how do we describe measurements in quantum mechanics? So you have probably seen from your quantum mechanics courses how to describe a measurement. So typically what you have is some Hamiltonian that describes the energy of your system. And the goal is to diagonalize the Hamiltonian, so find its eigenvalues. And the eigenvalues correspond to the energy of the system. And then what you would do is you would expand whatever state you have in this eigenbasis of the Hamiltonian, and then you'd find what the energies are at specific times based on the evolution given by the Schrodinger equation. So there, what the probabilities are given by the Born rule. So if you had some state psi, then basically the probability of being in some state E sub I corresponding to some energy is just given by this modulus squared, right? So we can write this actually more generally in terms of a trace as in this way. And we call this is just the Born rule, right? Now if you had a density matrix instead, or a mixed state, then we would just modify this in this way if you had a mixed state instead. So we would just write this as our Born rule. All right, so what we are describing here is a very specific type of measurement, which is called a projective measurement. So this is called and even more specifically, it is called, sometimes people will call this a von Neumann measurement. Call it a von Neumann measurement because this is a projection, but it's like a rank one. It's a rank one projection. So people call this sometimes a von Neumann measurement. So more generally, we could have, so for a projective measurement, more generally, we could have some projectors. So these are projectors in the sense that they are Hermitian. And they satisfy this, right? And so then our probabilities, the probability of obtaining the outcome corresponding to x when the state is rho, is that. All right, so this is for projective measurements, but there's actually a more general notion of measurements that we need when we talk about measurement and quantum information. And we can think about this more intuitively in a sort of physical way, where suppose if we want to measure some quantum system, how do we actually do that measurement in practice, right? So usually what we would do is we would take some other quantum system as a kind of probe. So suppose we had like a beaker with some water in it or some other liquid, and we wanted to measure its temperature. So how exactly would we do that? So we would take a thermometer and we would dip it into the beaker, and somehow the thermometer and the water inside or the liquid would interact, and somehow the dial on the thermometer would move up or down, indicating what the temperature is, right? So that is basically what corresponds to the more general notion of measurement, which is where we have some probe. We have our system that we actually want to measure. We interact our system and our probe, and then we measure the probe. Okay, so let's see what happens when we try to model a measurement in that way. So, so suppose we have some system. I'll just say that the state of the system is given by this density matrix, and we have a probe. So I indicate that by P. And And in order for us to measure, the goal is to measure the system, to measure properties of the system, right? But we're going to do that in a sort of indirect way by actually measuring the probe instead, right? So in order for us to do this, first of all, we need to interact the system and the probe. So we do that with some operation that we describe by unitary matrix. And then afterwards, we just measure the probe, right? And the measurement of this probe is in general going to be given by some projective measurement. Okay? So now let's see what happens when we do this. So first of all, what is the initial state? So the initial state before the interaction is just that. And then in the next step, what do we have? So we have right? Okay. And now we want to measure just the probe. So in order to measure the probe, we again use the Born rule that we have. So the probabilities of our outcomes. So the probability of obtaining the outcome X for this measurement is, so here now, because we're only measuring the probe, so what we get is this. Okay, so this is the state that we had, right? And this is our description of the Born rule when we only measure 1/2 of some bipartite system. So here we're only measuring the probe. So here we only put the measurement operators here, but here is just an identity matrix, right? And we take the tensor product, right? So now this is just some generic model. Ultimately, what we would like, because the system that we have, usually we don't necessarily do this in practice all the time. Mathematically, all we want to be able to do is, given this state alone, describe the measurement outcomes. So we would like something that looks like this for some operator m sub x that's acting only on the system, right? So if we simplify this, we can actually get it into that form. So here now we can use the cyclicity property of the trace. So use that. So what we're going to do is bring this u over here using that. All right. And now, so now we can think of this trace as being the full trace in the sense that we're tracing over both the system and the probe because we want to get a number out at the end. But what we can now do is simplify this a little bit. So we can write this in the following way. So maybe I write it over there. So okay, so we have that expression, and we want to get it to look like this. Okay, so we'll write it in this way. So yeah. Wait. What? Yeah. Yeah, so we want to yeah, so we want to make it look like this with the M. So how is M defined? So we can show that it is defined in this way. So in this way. So let's see how that comes about. So yeah, essentially we can think of this as being a trace over the system and the probe. So we take this and we bring one of these over to the other side using cyclicity. And then that basically gives us this expression. Okay? So here, so this is an operator acting on the system alone. Because we have this as a contraction between a bra and a ket. So I believe this will be now an operator acting only on the system. Right? So ultimately what we get is right now the point of all this was just to say that we can there's a more general notion of a measurement now, which is operators. It's fine. Let me just wait for that. Okay. One property I forgot to mention when I wrote this thing down was basically is this property. And this has to do with the fact that when we sum over all these probabilities, it should give us 1. And that's directly related to that. Okay, and we can show that this holds even here. So if we just take the definition of this and we take the sum over all x, we can bring that sum over x inside, and then we can use a property that these sum to the identity, and then we'll see that this whole thing collapses to the identity. So this is something that maybe we can see quickly. So right, I can bring the sum inside. And this is just identity, right? And because we have, I missed a unitary here and here. Let me just write it again. Okay, because this is now the identity on the system, and this is the identity on the probe. We have a unitary, so U is identity. And so this will just collapse to the identity overall on the system. So is that okay? So basically, all of this is just to say that this is a more general notion of a measurement in which these m's, they are not necessarily projectors in that way, right? So they are just some operators which are positive semi-definite, and they sum to the identity. And so in more mathematical language, we would call this, we also use this in quantum information. We call it a positive operator valued measure. Yeah, so this is some terminology that comes from mathematics, but and we usually abbreviate this as POVM. So this is basically the element that we needed, which is this more general notion of a measurement in which the operators that we use to get our probabilities, right? So this is now a new version of the Born rule in which these operators sitting here, they are not projectors necessarily. So they are just more general objects which are positive semi-definite and sum to identity. So this is how we model measurements in quantum mechanics more generally and also in quantum information. Okay. Yeah, I think this might be a good place to stop. So I think what we'll do next time is talk about quantum channels. So those are the key things that we need to start talking about quantum communication protocols. So I hope this was okay. Thanks.
Any question? I wanted to